symmetric domains.
Hi, can you all hear me? Good. So I would like to start by thanking the organizers for inviting me to speak here. It's a great honor, and I'm very happy to be here. So let me start by introducing the sort of main characters in my talk. X will be a hyperbolic Riemann surface of finite type, which simply means that we can write X as the difference of X bar minus a finite set of points, and X bar is a closed and has genus G. And I usually think of, well, a Riemann surface to look like that. Hyperbolic means that the universal cover of this Riemann surface is simply the unit disk. And very concretely, we can always express X as the quotient of the unit disk by a discrete group of automorphisms. Which acts properly discontinuously on the disk. So the unit disk is also equipped with a natural Poincare metric of constant curvature. -4, and I will denote the unit disk with this metric in this talk as, well, using the notation CH1 for the complex hyperbolic line. And of course, the Riemann surface inherits a natural complete metric of constant curvature. So since the automorphism group in this case coincides with the orientation-preserving isometries of CH1, and being finite type can also, well, it's also equivalent to saying that X is a finite volume. Okay, so the collection of all these Riemann surfaces forms the moduli space. So the isomorphism classes so I was warned I should write big. Is this good enough? Or? Okay. Good. And the modular space is known to be a complex quasi-projective variety. And let me introduce Teichmüller space as the universal cover of modular space. So Teichmüller space is, again, naturally a complex manifold of complex dimension 3G minus 3 plus n. And a remarkable, well, it's a remarkable theorem of Bers says that Teichmüller space can be realized as the simplest type of a complex manifold to simply bound its contractible domain in a complex vector space of the same dimension. And much like the Riemann surfaces themselves, modular space can be presented as the quotient of this bounded domain by a discrete group of automorphisms. Well, realizing modular space as a complex orbifold of finite volume for a natural metric on Teichmüller space, which I will be talking about shortly. So this is analogous to a more classical situation, and that is the situation of, well, that's the case of locally symmetric varieties. of non-compact type, or equivalently locally Hermitian symmetric manifolds. And they can always be presented as the quotient of a bounded symmetric domain by a discrete group of automorphisms. So let me remind you what a bounded symmetric domain means. I will give a complex analytic definition. It simply says that about every point there is a flip. There is a holomorphic involution for any point. There exists a holomorphic involution such that this point is an isolated fixed point. And of course, the class of these bounded symmetric domains coincides with the class of Hermitian symmetric spaces. But I would like to view them as bounded domains, as complex bounded domains for this talk, and forget the Hermitian metric. So a consequence of this definition, which might not be clear immediately, is that the automorphism group of this is very large. So it acts transitively. On points and directions. And well, the theme of trying to understand analogies between this class of well, symmetric spaces and Teichmüller spaces has been a major driving force in Teichmüller theory. There's two, well, so I won't say too much about it, but I want to mention two important things. One is that the simplest case, when the dimension of Teichmüller space is 1, then in fact they coincide. So Teichmüller space is simply the unit disk, biholomorphic to the unit disk, which again, simply the complex hyperbolic line. So it is a bounded symmetric domain. Also, let me introduce the notation of BSD to save my life for the rest of the talk. However, when the dimension is bigger than 2, bigger than or equal to 2, then the automorphism group of Teichmüller space is discrete. So this is a result due to Royden, at least in the case when we have no punctures. And moreover, there is no point about which Teichmüller space is symmetric. So there's no such holomorphic involution for any point. So it is very different globally from being a symmetric space. And Royden's idea for proving this result was to study the Kobayashi metric, the intrinsic Kobayashi metric on bounded domains. So and this is what I would like to do in this talk as well. So let me introduce the intrinsic Kobayashi metric. And formally, that says that any bounded domain is equipped with an intrinsic geometric shape. So let omega be some bounded domain. Then the intrinsic metric, the Kobayashi metric is simply the largest metric with a property that are all holomorphic maps from the unit disk or equivalent from CH1 into this domain. They are non-expanding. And let me just point out that this determines a norm on the tangent space. So it is a Finsland metric, but also a distance function on pairs of points. And let me just state what is the fundamental property of this metric. Is that all holomorphic maps between domains are always non-expanding. In their Kobayashi metrics. So this is just an analog. I mean, this is just a trivial consequence of the definition. It's an analog of the Schwarz lemma for bounded domains in any dimension. So before doing anything else, let me just give you some examples of what the Kobayashi metric looks like. In some cases. So in the case of the unit ball, the unit round ball, the Kobayashi metric is simply the complex hyperbolic metric. So it is a Kähler metric. It has constant curvature, holomorphic curvature. And coincides with a unique Hermitian symmetric metric on the space. But this is essentially the only case where the Kobayashi metric will be Riemannian. So, well, a particular example of that is when n equals 1, then we just have the unit disk with the Poincare metric. Another example is the bidisk, the product of two disks. In this case, the Kobayashi metric is the sup metric of the two factors. So in particular here, it's not Riemannian anymore. And the last example, which is due to Royden, it says that the Kobayashi metric on Teichmüller space coincides with the Teichmüller metric. And this is a fantastic result because the Teichmüller metric is, is accessible. You can understand geometrically its properties. So I haven't yet introduced what the Teichmüller metric is, so let me just do it now. So for any point in Teichmüller space corresponding to some Riemann surface X, there is a natural identification between the cotangent space to Teichmüller space over that point with the complex vector space of integrable holomorphic quadratic differentials on X. These are holomorphic forms of the form in some local coordinate Z. And this vector space is equipped with a natural norm. It has an L1 norm given by integrating this quadratic differential of the Riemann surface. And the Teichmüller metric is just the dual metric. So it is a Finsler metric given by the dual norm on tangent spaces. Okay, so let me tell you what I consider to be an amazing fact. Although the Teichmüller metric, the Kobayashi metric on Teichmüller space and bounded symmetric domains is practically never Hermitian, these spaces are abundantly populated by holomorphic complex hyperbolic lines. So let omega be Teichmüller space or BSD. Then for any point and direction, there exists a holomorphic map passing through this point and in that direction, which is a totally geodesic isometry. Meaning that it locally preserves distance of points, or it sends unit geodesics to unit geodesics. And in the case of Teichmüller space, these totally geodesic isometries, they are called Teichmüller disks. And they are related, they arise from a natural from the natural SL to R action on the bundle of quadratic differentials. So a folklore problem in this, in Teichmüller theory for a while was whether being a totally geodesic isometry is enough to guarantee that you're a Teichmüller disk. That is, it's a holomorphic totally geodesic isometry. And the first theorem I would like to state settles this question, this problem. So let F be a totally geodesic isometry. For the Kobayashi metrics. So I will skip this word. I would always refer to the Kobayashi metric and the Kobayashi isometries. Well, then, in fact, F is holomorphic. Or anti-holomorphic. And in particular, it is a Teichmüller disk. And the assumptions on F here are very weak. All I know is that it's an isometry. I don't start with any other assumption, even being differentiable. So all I know is that it preserves distance of points. So let me make one remark that this was known to be true if we replace Teichmüller space with a bounded symmetric domain of rank 1, which are just the complex hyperbolic spaces. However, it fails in higher ranks, so it's false if the rank is at least 2. And it has to do with the supremo metric on the product of 2 bidisks, essentially. So in fact, the theorem I proved, it holds for a fairly large class of boundary domains, including CH1s and Teichmüller spaces. And I hope to sketch the proof later. Okay, so that settles what happens in dimension 1. So the next question is what happens when the dimensions are at least 2. And let me just start by noting that there are many holomorphic isometries between, well, for now I will just restrict to considering holomorphic isometries. So it is known that there are in fact many holomorphic isometries between bounded symmetric domains and Teichmüller spaces. So and that for any bounded symmetric domain and any Teichmüller space, you can always find, well, as many as you like other bounded symmetric domains with holomorphic isometric maps like that. However, the next results I will state show that when the dimension is at least 2 bounded symmetric domains and Teichmüller spaces, they do not mix at all in their Kobayashi metric. So in particular, there is no holomorphic isometry from a bounded symmetric domain into Teichmüller space or from Teichmüller space to a bounded symmetric domain. And here by holomorphic isometry, I don't require F to be totally geodesic. All I want is to preserve the norm. Okay, so let me just state as a separate theorem a special case of that, which I think is already interesting on its own. That there is no holomorphic isometry from CH2 into Teichmüller space. And we also prove a similar theorem for isometric submersions. So let me say that, well, if omega and TGN are as in theorem 2, then there is no holomorphic isometric submersion between bounded symmetric domains and Teichmüller spaces. And by holomorphic isometric submersion, I mean a holomorphic map such that the dual of the differential is an isometry for the dual norms. Okay. So let me make several remarks about theorem 2 and 3. So it is known that there exist many holomorphic there exist Teichmüller curves. There are many Teichmüller curves in moduli space. And by Teichmüller curve, I mean isometrically immersed hyperbolic Riemann surface of finite type. Or and the existence of such curves has a lot of applications to the theory of billiards. So one of the main motivations for proving theorem 2 is the following immediate corollary that says that there are no higher dimensional analogs. That is, higher dimensional locally symmetric varieties. Isometrically immersed in MG. And in particular, no complex hyperbolic varieties. So the second remark I want to make is, well, there exist holomorphic maps from Teichmüller spaces into bounded symmetric domains. So the simplest one is the Torelli map that sends a Riemann surface to Jacobian. And it's a holomorphic map into the Siegel space. Which is a bounded symmetric domain. These maps are known to be strictly contracting in most directions. And the third remark has to do with theorem 3. In fact, there are holomorphic isometric submersions of Teichmüller space onto the complex hyperbolic line. And they are given by holomorphic retractions onto abelian Teichmüller disks. So in particular, that shows that the restrictions of the dimensions are necessary for that result. Okay. Are there any questions? Or?
Sorry, could you say what 3 is again? What's the example?
So for any abelian Teichmüller disk, any Teichmüller disk generated by the square of holomorphic one form, there exists a holomorphic retraction of Teichmüller space onto this disk. And they're given by normalized periods. Alternatively, there are some directions where the Torelli map is isometric. And these are exactly these abelian directions. And projections, holomorphic retractions exist for bounded symmetric domains. So what I would like to do for the remaining of the talk is try to sketch the ideas. I will try to focus on theorem 1 and theorem 2 prime, and try to sketch the ideas. And if I have any time remaining, I would also want to mention a few open problems in this direction. So although technically the proofs for theorem 1 and theorem 2 prime are very different, they both use one common idea, which is that of complexification and realification. That is, in the first theorem, we'll try to complexify, and in theorem 2 prime, we'll try to do the opposite. So let me just describe an instance of that in the study of Teichmüller geodesics, which will be important in the proofs. So let me recall that for any quadratic differential on a Riemann surface, there is a Teichmüller disk. That's a holomorphic isometry from CH1 into Teichmüller space, which arises from this natural SL2R action. And very concretely, the quadratic differential allows us to express this Riemann surface as a finite polygon in the plane, with pairs of parallel sides identified by isometries. And then the linear action of SL2R on the plane just acts on these polygons. But for any quadratic differential, there is another interesting geometric invariant, which is a pair of transverse measure foliations on the Riemann surface. And concretely, in a coordinate chart where the quadratic differential takes this form, this is just simply the measure foliation given by vertical lines in the plane. And the transverse measure is simply the total variation in the x direction. So you can just pull back the complex, the vertical lines to the surface and get a measure foliation. And it will have singularities at the zeros of this quadratic differential, but otherwise it's a nice foliation. So in particular, this map is known to give an embedding of this bundle of quadratic differentials inside the product of the space of measured foliations. Up to an equivalence relation. That is, you would like to identify two when they differ by an isotropy preserving the transverse measures or by splitting the zeros. And moreover, this space has a natural continuous function, the geometric intersection pairing. Which generalizes the geometric intersection of simple closed curves. And it encodes the Teichmüller metric via this nice formula. Oops. And whereas this complex Teichmüller disk arises from this SL2R action, here we only see the real structure. So we lose all the information we had about complex geodesics. And that gives us two distinct ways of understanding Teichmüller geodesics. So the first one, coming from the, let me first start. Given any unit geodesic, there are two ways you can describe it. One is via this SL2R action, which the opposite of that is that there is an extension. There's a complexification. Which is holomorphic and totally geodesic. And it's described very concretely in terms of this SL2R action. And the other way is in terms of measured foliations. And in this case, there's a lift, the canonical lift. Is simply given, is described by a very simple form. in terms of this embedding, which provides a very convenient way of understanding the real geodesics. Okay, so both of these descriptions will take part in the proofs of the theorem. So let me just start by trying to explain that. So in the first case, we start with a totally geodesic isometry into Teichmüller space. So in particular, that means that any geodesic here will map to a Teichmüller geodesic. And this Teichmüller geodesic extends to a holomorphic isometry of CH1 inside Teichmüller space. So the idea is to try to or organize all these Teichmüller geodesics into a new map. So in particular, we would like to forget the complex structure here, and we embed it as a totally real diagonal inside this bidisk. And then the first step in the proof is that we extend F using the Teichmüller disks to a map on this bidisk. And how does this work? Well, for any geodesic, any real geodesic in CH1, there exists a holomorphic complexification inside this bidisk. And then we define F on this CH1 to be the Teichmüller disk. And the important point here is that these complexifications, as gamma runs over all geodesics in CH1, they foliate this bidisk, at least in the complement of this totally real diagonal. Okay, so now having a well-defined map, the second step of the proof is to prove that this map is holomorphic. And that's certainly an obvious thing. A priori, F need not even be differentiable, let alone real analytic. And that involves an argument in complex analysis, so I will not talk about this step. But what do we get once we know that F is holomorphic? Well, then we have a holomorphic family of disks. And what we prove, assuming that this F was totally geodesic, so let me just denote the bidisk as a square. There exists a slice which is either horizontal or vertical. Such that F restricted on this slice is unbounded along a positive set of radial lays. And let me just note something. Well, these slices are, of course, not totally geodesic. So the yeah.
Just say once again the construction. How do you construct a big map to capital F?
Right. So for any geodesic here, it complexifies to give you a holomorphic map from CH1 inside here. And that is simply given by the graph of the reflection, if you like, with respect to the geodesic. Any geodesic gives a reflection, and the graph of this reflection is the holomorphic extension of the real geodesic here. And then on this slice, I just define the map to be the Teichmüller disk. And the reason this is all defined is because all this, I mean, this will intersect along this totally real diagonal, but because we have a well-defined map to begin with, this contraction gives a well-defined map. Well, another way to think about that, if the image of this map was not a Teichmüller disk, it would have to be some totally real isometric plane in Teichmüller space, and then it's sort of Teichmüller disk intersected everywhere. And then what this map does, organizes this into a holomorphic map. Okay, so the horizontal and vertical slices here are not, the F does not restrict to an isometry. So it's not clear, well, in principle, why this should be true. And indeed, the fact that F is totally geodesic is very important in proving that. But once we know that, then we are done, because we don't just have one slice, we have a whole family of slices. But then these particular holomorphic disks, well, the radial layers, almost all of them, will converge to totally degenerate points in the boundary of the Bers embedding. And Sullivan's theorem says that these are rigid, you can't move them. So it follows by Sullivan's rigidity theorem that F restricted on all parallel slices is equal to this. Well, F agrees on all these parallel slices. Which is essentially what we wanted to prove, because this is a holomorphic map and it's totally degenerate. The image is a Teichmüller disk.
So wait, the F, capital F, exists because of, where do you get capital F?
Oh, just because of the existence of Teichmüller disks.
It's defined on the product?
Yes.
I see. Is that a diagonal embedding?
It's a totally real diagonal embedding. So I take the opposite complex structure here so that the graphs are holomorphic. I mean,
Could you repeat what 3 says? It starts with,
well, we have this product structure, and then we have this holomorphic slices, the vertical and the horizontal ones. And I claim that either some vertical or some horizontal one have the property that when F is restricted on them, it is unbounded along a set of positive measure, along a set of radial rays of positive measure. Now these rays,
Why is that?
that's non-trivial. That's not trivial. In fact, it has to do with the fact that just right over here, the point Z, W lies on a complexification of a geodesic if and only if the point W, Z lies on this complexification. So I mean, it's a trivial fact, but actually this is exactly what is hidden behind this proof. The reason is because the distance between these 2 points in the Kobayashi metric of the product is going to be equal to the Teichmüller distance between Z and W. So you know that, oops. Sorry. That's supposed to be a sketch, so I'm happy to feed it.
F is anti-holomorphic on CH in the
Yeah, it's holomorphic here, which means if you change the complex structure, it's holomorphic and anti-holomorphic. Which is exactly where this either or.
Wait, what's the bottom is that it can't be? I've lost the overall.
I interrupted you answering him.
Sorry?
You were answering Hernandez's question, and I interrupted and didn't finish it. So he asked what 3 was.
Yes.
And then, or whatever.
So, did I answer the question? Or? Happy to talk more the details afterwards. So let me just sketch the proof of 2 prime. Well, there we start with a holomorphic map from H2 into Teichmüller space. The holomorphic isometry. The idea is to do the opposite, to restrict this map. To a totally real. So we restrict totally real and totally geodesic. Okay, that step is easy. We can do that. But what do we get from that? Well, let me draw a picture. So this is the image of this totally real hyperbolic plane in Teichmüller space, which is a totally geodesic subset of Teichmüller space. And I considered 2 orthogonal geodesics generated by quadratic differentials x comma p on a Riemann surface and x comma q. Then the idea is to explore, to exploit, to use the asymptotic behavior of the geodesics to relate the complex hyperbolic horocycles to level set of extremal length. And the reason we can do that is due to a theorem of measure saying that once these are chosen to be generic enough, for example, the vertical foliation of both quadratic differentials are uniquely ergodic and minimal, then there is then this method works. And indeed, we can describe these complex hyperbolic horocycles as being level sets of extremal length for the corresponding measure foliations. So the upshot of this discussion is that we have a very nice description, geometric description of the geometric intersection pairing between these 2 measure foliations, which is simply given by this formula. It's described in terms of the distance of these 2 points. So what we do next is just start varying this totally real slice. So we vary it so that it contains, we keep fixed one of the geodesics, and we vary the orthogonal one inside the Teichmüller disk. Then, because of the symmetries, because this can be realized by a holomorphic map of CH2, it follows that this distance doesn't change. So in particular, a consequence of that sorry, let me just is that the geometric intersection pairing between these two foliations does not depend on the angle. It's independent. And we conclude the proof by proving that this is impossible. By a direct geometric, get a contradiction. By the geometric argument on the Riemann surface, we prove that this expression is never independent of the angle. In fact, it is given by the following formula. So it is never independent of the angle, and that's where the contradiction comes from. Okay, so that was a brief sketch of the proofs. Are there any questions? Okay, so in the remaining 5 minutes, I would like to briefly mention some open questions that I would like to know the answer, and that it would be interesting to solve. Well, the first one is about theorem 1. Is theorem, well, is every isometry C1 isometry? And by isometry here, I mean a local isometry for the Kobayashi norms. Is it a Teichmüller disk? The problem is that such a map will not necessarily map geodesics to geodesics. So this argument doesn't apply because there's no good way of extending this map. So the second question is, the proof of theorem 2 uses the global geometry of Teichmüller space. It will be an interesting challenge to try to find an infinitesimal proof. So is there a local isometry? Is there a linear isometry? From the complex 2-plane with the round metric to the tangent space over a Riemann surface with respect to the Kobayashi metric. And let me just mention here the theorem that there are no linear isometries on the dual metric, so on the quadratic differentials with the L1 norm. And what this question asks is whether one can actually find isometric submersions onto, well, from this space onto this. It's a more concrete way. And this is an essential ingredient in the proof of theorem 3. So let me mention one third question, which is a geometric version of this. Is there a holomorphic map from a Hermitian manifold? That is an isometry for the norms. It's a local isometry. Again, as a positive indication for that, sort of a corollary of theorem 2 is that the answer is no. If this is assumed to be Taylor with either holomorphic curvature being bounded below by -4, or F assumed to be totally geodesic. However, in general, I don't know the answer. let me just mention one last problem, and that is this theorem 2 true for infinite dimensional bounded symmetric domains. It's probably the most interesting out of the four. So this is equivalent to asking, given any Teichmüller disk, is there a holomorphic retraction on this Teichmüller disk? And yet another equivalent way to ask is whether the Cartesian metric coincides with the Kobayashi metric. And I think I'll stop here.